Okay, yeah, welcome back. So if you joined us from the last video, we looked at this same plane stress element and we did a rather arbitrary transformation of stresses. So we were able to use our formulae for transforming stresses and look at what those stresses would be. It's a somewhat arbitrary angle theta. So in this case, we're going to be a little bit more pointed and we're going to look for the principal stresses. And of course, by principal stresses, we're looking for where the normal stresses are going to be a maximum and a minimum. And that will, of course, feed into our evaluation as to whether the material is going to be able to withstand that stress or not. We're also going to take a look right at the very end and say, okay, what about the plane where shear stresses are maximum and what's going on there? Because, of course, they're all related and it's all good information to have. So the first thing I'm going to do is we have our plane stress element is I'm going to determine what the orientation of the principal plane is. So okay, so this is fairly straightforward. We have a formula for this. So we're going to look at tan 2 theta p, and that's going to be equal to 2 times tau xy, all divided by sigma x minus sigma y. And of course, these have all been derived in class. So we have 200 times our 200 kPa, and that's a positive value. We went over that in the last video, so hopefully that's not a surprise to you, as are the two normal stresses. They're both tension, so they're both positive. So 300 kilopascals minus 100 kilopascals, and that gets us an angle theta p equals to, oh, sorry, be careful here. That's tan 2 theta p, blah, blah, blah. So therefore, theta p is equal to 31.7 degrees. And that's a positive value. And so by being a positive value means that it's going to be going counterclockwise. And so just to keep that reinforced in our mind, I'm going to go and draw the element where the principal stresses are going to occur. So that orientation of 31.7 degrees. So there we go. I've drawn out the element in the orientation of theta p. I've labeled it with theta p, drawn in my new axes x prime, y prime, as before. And so what I need to do now is label this and say, calculate our principal stresses. And they can be sigma 1, sigma 2, sigma max, sigma min. There's a different nomenclatures used in different places, all meaning the same thing. And so our sigma max comma min is equal to our sigma x plus sigma y divided by 2, and then plus or minus the square root, it's a big one, of sigma x minus sigma y over 2, that's squared, plus our tau xy all squared. And so I'll substitute in our values. And so we have our 300 kPa, and you want to give some effort to make sure you get the signs correct in here. That's a fairly common mistake. People don't follow the sign convention. That's plus or minus square root of 300 kPa minus 100 kPa divided by 2 That's all squared, plus 100 kPa, or sorry, 200 kPa, all squared. Extend that square root sign out. And I'm going to, and I'll talk to it later, but I'm going to write them down into their individual components. So that's 200 kPa plus or minus 223.6 kPa. And so that's equal to 423.6 kilopascals and minus 23.6 kilopascals. So it is often possible to determine which one is sigma max and which one is sigma min. By that I mean, is it sigma x prime sigma max or is it sigma y prime sigma max? But the fail-safe way to do that is to check the orientation by using our formula from the last example for sigma x prime and calculate it out. Now that we know the orientation, so that's sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 cos 2 theta plus tau xy sine 2 theta. And so we'll fill those out. We have 300 kPa plus 100 kPa divided by 2 plus 300 kPa minus 100 kPa divided by 2. That's cos 2 times 31.7 degrees plus our tau xy, which is 200 kPa sine 2 theta, which is 2 times 31.7 degrees. That gives us a value of 423.6 kPa, which the whole reason why we did that was to determine where was sigma max. So sigma max is 423.6 kPa, and now we know that's oriented to x prime and not y prime. So I'm going to go ahead and draw those stresses in here. So we have sigma x prime or sigma max of 423.6. It's positive, which tells us that it's in tension. So it's going here in tension. It's 423.6 kPa. And sigma min is negative 23.6 or compression. And so it would be on the y prime. It's on the other face or other axis, if you will. And so we'll draw it in as compression. And give it a value of 23.6 kPa. And because these are the principal stresses, we also know that the shear stress on the principal plane is equal to 0. So there is no shear stress. There is no tau x prime y prime in this orientation because that's where the principal stresses occurs, where the shear stress is equal to 0. But it is worth asking yourself, this is okay, we would like to calculate what the maximum shear stress is, so tau max, and its orientation. So a couple things worth noting, and we may as well write it out here and say, note that our theta tau max is plus or minus 45 degrees from theta p. So we're able to actually figure out what that orientation is. And so we just take our 31.7 degrees, we subtract 45 degrees, and we're going to get an angle of minus 13.3 degrees. So I'm going to go ahead and draw that in, and then we'll talk about figuring out what tau max is. So I've drawn in my orientation for where we're going to have tau max. And so I've got that. I've got a negative 13.3 degrees. And I'm going to just write out the formula then for our tau max. And it is equal to sigma x minus sigma y all over 2 all squared plus tau xy all squared. And while I'm at it, I'm going to say the normal stress occurring on that orientation, so theta for shear, is equal to our average normal stresses, so sigma x plus sigma y all over 2. And before I go ahead and plug in the values, one thing I want to do is I want to go back up to where we calculated our maximum and minimum stresses and point something out. And so if I look at this component in the root, we see that that is equal to our tau max. And when we look at the other component, that is equal to our sigma theta s. And so by having done that, by having calculated them out and kept them independent so that I can see what those actual values are, I can shortcut the process a little bit and just write them in here. So tau max then is equal to 223.6 kPa, and our normal stress at theta s is equal to 200 kPa. And there's no sense in redoing those calculations if we've already done them before, and we know we've done them before because we know enough that those two terms exist in that other formula. And so the last thing I need to do then is to put them on my new element. And so I'll start with my normal stresses. And so it's tension, 200 kilopascals, and that would occur on all 4 of the faces. And so I can put that in here, tension, and that's 200 kPa. And tau max then is 223.6, so it's positive. So if I go to my x prime positive face, positive direction, we're going up in this direction, which means we're coming this way, pinching into opposite corners. And the value there is 223.6 kilopascals. And that's all there is to doing the principal stresses. Of course, in the shortly, we're going to look at Mohr circle. We have some examples of Mohr circles. Maybe I'll put a card up here in case that's what you're looking for is a Mohr circle example. I do have one done up, so I will put up a link to it. For our purposes, this is all we're doing at this point in time is applying the formulas and understanding what they mean. So there you have principal stresses. And of course, these are really, really important when it comes to looking at our failure criteria. We're going to need to know what our principal stresses are to compare them to the material properties and figure out if it's going to fail, because it matters when we have more than one stress in different planes. They interact in really interesting ways. So hopefully you found that helpful. You're able to now follow it through and to redo your own calculations because it's going to be really important as we move forward. So I will leave a link to the next sample. We're back into some more combined load examples, some more complex combined load examples, and I invite you to follow along with those and extend your skill in this area.